Welcome, everyone.
Hi, everyone.
I think looks like we're right on time to go ahead and get started. So we want to thank you for joining us today for this first of our kind of live webinars for the academic community and interested in learning more about vibrational spectroscopy and specifically FTIR and Raman fundamentals. So before we get started, I just want to kind of lay out sort of the structure for how we're going to spend the next hour. So I will, we'll kind of ask you to stay on mute. And if you have questions as we go through the first part of the presentation, feel free to put those in the chat. And then, as I present for the first part, my colleague Sudhir will be kind of monitoring if he sees there's a question I should, address straight away and stop, he'll interrupt me. And likewise, when he's talking, I'll kind of do the same thing. Our goal is to spend only about a half an hour or so presenting, and then we'll open it up for to address the questions in the chat and have some discussion. So if there's anything we don't get to today, we'll be able to follow up with you after this. And, this is the first in a series, so we're going to be really just talking about some fundamentals and hope you'll be able to join us for the upcoming sessions. So Sudhir, is there anything I forgot here before we get going on today's topic?
Yes, the meeting is being recorded and it will be available later on viewing in our website.
Yeah. All right. Anything else?
No, that's it. Let's do
it.
Yeah.
Yeah. So today's talk, as I said, we're really just going to be talking about the fundamentals of FTIR and Raman. So, hopefully you'll kind of find, we're just going to lay a good foundation. We know we have a broad audience here. So if you can find the reaction buttons on Teams here, if you're an undergraduate student, go ahead and put a thumbs up. I'd be curious to know how many undergraduates we have in our audience today joining us. And if you're a grad student, you can go ahead and do a reaction, or if you're a professor, just interested to see who's all joining us as they kind of start the presentation.
Yeah, I see.
Do you see?
Yeah, thumbs up and claps going up. Yeah.
All right, I can't see the reactions when I went into presentation mode, so thanks. Just some real quick introductions. So my name is Lena Woodis, and I did my PhD at the University of Wisconsin in Madison. And I did my PhD in ultrafast coherent multidimensional spectroscopies, which is a mouthful. But basically, we were developing these techniques that involved multiple ultrafast pulsed lasers to look at the quantum state structure of novel nanomaterials. And we were collaborating with materials science groups to look at new materials for solar cell technology. And then I spent just over a decade as a professor. So I taught a lot of general chemistry, physical chemistry, instrumental analysis, and had a lot of fun doing that. And always, developed a love of instrumentation and measurement. And so I decided to make a transition into the business world because I was always kind of curious about that and advising students and things for other careers outside of academia. And I joined here at Thermo Fisher Scientific. I'm based in our Madison, Wisconsin site, where we manufacture all of our FTIR instruments, as well as have the research and development team and our product support team for around the world. And so I really love this career now, where I work with scientists all over the world, learning about what their needs are, as well as getting to work with the research and development and testing, and also just the fascinating world of operations and the manufacturing of these, technical instruments. So I'll pause and let Sudhir introduce himself.
Yep. Thanks, Lena. Hi, everyone. Good morning, good afternoon, good evening, wherever you are. Thanks for attending. I am Sudhir Dahal. I'm the product manager for benchtop Raman spectrometers and Raman microscope here at Thermo Fisher Scientific, also based in Madison, Wisconsin site. So Lena and I belong to the same bigger group. And we, in terms of roles, as he described, my roles are very similar, just managing different sets of instruments, on the Raman side. I got my PhD from University of Maryland, Baltimore County. And in my graduate study, I worked on developing a novel method of multi-photon photoacoustic spectroscopy, also mouthful. And then the application was for brain tumor detection and imaging. While in my college and grad school, I worked on various, variety of spectroscopy technique, and as you all know, obviously a lot of analytical instrumentation. I just love working with the instruments. I transitioned to industry directly after my PhD and have spent about 10 years now. In my current and previous roles, I very much enjoy teaching and then training users of various levels, from students to people who have been in the lab or even on the business sides for many years. So over the years, I've stayed in touch with students and professors in universities, attended conferences, and interacted with students, during career events and similar other events. For my presentation today, I'm really excited and looking forward to all the interactions we're going to have. Thank you. Back to you.
Great. All right. So just to kind of give you an overview as we get into this, as I said, we're recording the presentation. I believe this will be shared out with you, afterwards. So I know some of the slides might have a lot of content that we go through quickly, but this is our instrument portfolio. Again, all the instruments that we manufacture here in Madison, Wisconsin, that serve various points in the industrial processes of manufacturing materials, or doing failure analysis, research and development, in almost any kind of industry you can think of. So we have a lot of infrared instruments, and we also have some Raman instruments, and so that's what we're going to be talking about, those two different types of spectroscopies today. And as I said, one thing again that I really love about spectroscopy is just how widely applicable it is, because it is so foundational to understanding materials and what they're made out of. And so, any sort of company or industry you can think of that uses materials, does reactions to turn them into other things, or, manufacturing components that utilize incoming, raw materials and things like that, from, also food and beverage, to, pharmaceuticals, of course, to forensics labs. All of this is using often FTIR and Raman spectroscopy at some point in their process to understand the materials and make those products safe, and optimize their processes. So the reason why molecular spectroscopy is so foundational is what I love to say. There was a textbook that I used to teach out of, so I can't claim this mantra, but I did take it on, is structure determines function. And so you learn in chemistry from day one that if we can understand how a molecule, how a material is put together, and then a chemist wants to then understand, what that structure then means for its function and how we can manipulate it. And so FTIR spectroscopy will tell you what that material is made of. So chiefly, it's a material identification tool, but that's not all it can do either. You can, also use it to determine how much material you have, and again, in exactly what form it is. This is also a really great technique because it's really easy to do. There's very little to sometimes no sample preparation. You can do these experiments very fast. We'll explain the interferometer. It makes these measurements very quickly, and there's often, it's non-destructive to the material, and you can analyze just about anything. And so these measurements. This analysis can happen from, research development stages all the way through manufacturing to quality control, as well as failure analysis. The spectroscopy at its very roots is the study of how light interacts with matter. And so again, something that's probably familiar to most, if not all of you, is the electromagnetic spectrum of light. And, different regions of this spectrum will probe different characteristics of a material. And so for FTIR, the IR stands for infrared. And so we are using light that has the infrared frequencies. And the infrared frequencies will interact with molecules that have motions that change what's called the dipole moment of that molecule. So again, from general chemistry days, you probably know what a polar bond is, and therefore you can, analyze the bonds in a molecule to determine if a molecule is polar. And then those corresponding molecular motions, the vibrational modes they're called, will vibrate at these infrared frequencies. And so when infrared light is shined on a material, and if that frequency is resonant, has the same frequency as one of these motions, then that material will absorb that light. And so by looking at what frequencies of light are absorbed by a material, then we can deduce, analyze what the structure, what frequencies, what modes were part of that material. Now, just like different parts of the overall electromagnetic spectrum, we'll look at different types of molecular motion or material characteristics. Within the infrared, there's also sort of target parts of the infrared spectrum that will answer specific types of questions. So the heart of the IR region is called the mid-IR region. And often you'll see FTIR, vibrational spectroscopists will talk in terms of wave numbers. And wave number is an energy unit. And so from about 400 wave numbers to 4,000 wave numbers is considered the mid-IR region. And this is where you have those frequencies of what are called the fundamental molecular modes. And so this region is used for identification. Again, the peaks that are present in an IR spectrum correspond to the structure of that material. And many parts of this are pretty, you can assign peaks to different modes, are also compared to libraries to identify a material. On the lower energy side of the mid-IR, we have what's called far IR. Those terms come from how far away from visible light we are. And so far is getting further away from visible. And here, these are lower frequency modes. Think oftentimes it's like lattice vibrations. So you have a crystal structure or some sort of regularly structured material. It has some lower frequency modes that are not just a single molecule moving, which are higher frequencies, but these long range kind of motion. And so this often happens in minerals or other inorganic materials, some polymers, overall polymer structure and things like that. So the far IR region is of interest. And then again, on the other side, so the higher energy side of IR, we have near IR. And here, these bands are weaker because they are not interacting directly with the fundamental vibrational modes, but it's rather the overtones and combination bands. So when two fundamental interactions interact with each other, then we have these overtones. Think harmonics, right? So here, this region is useful because the bands are a weaker absorbance, you can actually probe a bit deeper into the material. And so you can analyze materials that are not great for analyzing in the mid-IR. And I'll say a little bit more about that later. So just to put all of that in sort of a more visual context, across the infrared spectrum, you can find characteristic functional group frequencies. There's even a part that's called the fingerprint region. It's often a complex spectral, lot of complex spectral features, but the exact peaks that are there are often unique from one material to another. And so we say it's like a fingerprint. And again, by comparing to libraries, databases of known materials, you can identify a material based upon that. And then further out, you can see like here, like a carbonyl mode. He is a very strong peak at a well-known frequency, and CH stretching modes. And so this is how infrared spectroscopist can use the infrared spectrum to identify a material. Now, the heart of an FTIR instrument, the FT stands for Fourier transform, and the measurement is actually made using the interferometer. And so the interferometer is based upon a structure that was designed by Michelson. So it's called a Michelson interferometer. And it works based upon interference of light, hence interferometer. And so what we have is a optical material called a beam splitter. That's the gray piece in there. And you have two mirrors. One of them does not move, called the fixed mirror, and one of them moves. Now, we take our infrared source light, which is a thermal kind of glow bar source, and so it has all the frequencies of the infrared spectrum within it. And if we shine that source into our interferometer, it's going to hit this optical material, the beam splitter material. And that beam splitter is called a beam splitter because it will reflect a portion of the light to the fixed mirror, and it'll transmit a portion of the light to the moving mirror. And we call scanning in an interferometer moving this mirror back and forth. And as that mirror scans, it changes the path difference for photons that are reflecting and transmitting and then coming back to the beam splitter. And so you get these interferences of the light as it comes back to the beam splitter and then goes ultimately then toward the detector. So we have this so-called modulated light. You'll see we have a Heaney laser here. The laser is used not as any source to interact with the sample. It is controlling the moving mirror. And so we get a consistent scanning speed, and we can control the way that moving mirror even steps if we want it to by having the Heaney laser. So if the laser's not on, this moving mirror does not scan. So now we have this modulated infrared light that is headed toward a detector. And if we place a sample in there, we can, at a most simple experiment, determine the absorption or transmission, depending upon which way you want to plot it. So to kind of diagram that out just a little bit more, we have the interferogram, and maybe you've seen these. So you can model an interferogram yourself by adding together a bunch of sine waves of different frequencies. And as you add more and more together, you get this interference pattern. And there's a big zero crossing where there's constructive interference. You have what's called the ZPD, and so that's the big peak in the middle, and then you have the oscillations on the sides. And so all the frequencies of the infrared light are embedded in this interferogram. And so to extract them out into the sort of spectral view, then the wave number space, we do a Fourier transform. So it's essentially an integral over all those sine wave frequencies, and we get what's called the single beam. And so this single beam is showing you the infrared light characteristics that are getting to your detector. And in this case, this is a single beam. The background is when I don't have anything obstructing the light coming from the interferometer to the detector, or I have everything but my sample, if you will. And so in this case, I've got a diamond crystal, and I'll explain why that is often useful. And so I've got some absorption, and then I've got water and carbon dioxide peaks in there as well. And that all might look like it's problematic. But what we do is we take that background so that we have all those signals that we're not interested in. We then make the measurement again by putting our sample in the light path. And so we get another one of these single beams. And you might notice now, especially if you look here, right? There's more features now in the single beam with my sample in place than before. And so depending upon what type of final format you want your data in, again, most simply, percent T is the transmission. You can also turn percent T into absorbance, which is what I'm showing here. So essentially you ratio these two, and then you can do any other sort of processing you want for what you want your final format to be. And so the peaks now that are here in my absorbance spectrum are the peaks only due to the sample material. Just a couple of things I wanted to show real quickly, because again, I think especially for undergraduates and even maybe some graduate students too in our audience today, there's so many different sampling methods and accessories that make these sampling methods really easy to use. And so depending upon your material, we were, Sudhir and I were talking, when we were undergraduates, really all we were exposed to, even at this level, was putting your sample between some salt plates. But there's so many more sophisticated ways that you can utilize FTIR now. And one of the main ones is ATR. And so I'm going to say a little bit about ATR. There's also, you can measure reflectance. So it's called diffuse reflectance. You can use a special kind of way of detecting the light that comes either from transmission or reflection using an integrated sphere. So that's useful when you have kind of weak signals and you really need to capture all the light coming out of the sample. We also have fiber probes. So for cases in an industry where you want to measure your material, say in a reactor, or you have an incoming, raw materials and you need to just kind of sample and probe those things in bulk, that's what these fiber probes are really useful for. And all these accessories enable, measuring evolved gas. So that's this, you can see this black transfer line. You can measure liquids, so you can do ATR in a trough. Really, the sky's the limit. So a little bit on ATR. So ATR stands for attenuated total reflectance. And after its development, it really just became ubiquitous. It's one of the easiest sampling methods out there because you can put any solids on there, you can put liquids on an ATR. And what happens with ATR is here's what the accessory often looks like, some version of this. You have a puck, that's the metal kind of disc there, and embedded in that puck is a little crystal. And depending upon what kind of measurement you want to do, what your material is made of, you might choose different crystals. And so what I'm presenting here is for a diamond crystal, because diamond, again, with some absorption bands in the mid-IR, it does have a wide range in which you can, it'll transmit light. So what you do is you place your sample on top of that crystal, and the infrared source light actually comes up from underneath the crystal. So it comes into the accessory here. There are mirrors that shine the light up, and then it gets reflected from the interface between the top of the crystal and the sample back down and goes to the detector. And so what you're actually measuring then is the reflected light from the crystal if there's no sample on top, so just air, versus when you put your sample on there. Because what happens is when that light hits the top surface of the crystal, there's a little bit of transmission. And that transmission goes into your sample, and it turns into what's called an evanescent wave. And so a little bit of the energy, right, some of these photons from your incoming light are going into this evanescent wave. And so there's a little less light coming back out. It's not 100% reflection at that interface. So that's why it's called attenuated total reflectance. And so when you can take, again, that ratio of sample to no sample, then you get peaks that are due to how that light interacted with the sample on top of the crystal. Now, because of the nature of this evanescent wave going into the sample, the depth of penetration of that evanescent wave changes with the frequency of the infrared light. So in other words, not all of the photons, will penetrate and interact with the sample to the same extent. And I can kind of, again, we'll send this out later, so you don't have to look at all of this in detail, but I just plopped the equation for how that's calculated. And basically we're seeing as the wavelength is increasing, the depth of penetration is also increasing. If you have very short wavelengths or higher energy, then there's a very tiny interaction with the sample. Okay, so ATR is not always useful on the extremes of your infrared spectrum, but it can be, depending upon your material. So, but for mid-IR, it's extremely useful, and oftentimes for far IR as well. And it's just important to know that if you want to compare absorption spectra, an absorption spectrum taken with transmission is going to be a little different than taken with ATR. And the reason is that depth of penetration. And so with transmission, you have a constant path length because of the thickness of the sample is the same and all of the light goes right through it. In ATR, all of the frequencies are not interacting with the sample to the same extent. That depth of penetration is changing across the spectrum, and so it's more like a variable path length across your spectrum. But because that variation is well understood within the software, if you want to, you can apply a correction so that you can still take ATR spectra and compare to libraries of sort of regular absorbance spectra, if you will. There are also a lot of libraries now for ATR spectra because ATR is so widely used. Lastly, I'll just say a couple of things about the near IR measurements. And really this is because there were a couple questions in the beginning, and so I'll put this up here. You know, again, this is utilized a lot in pharmaceutical process and polymers. So I'll have this up here and we can talk more about in the Q&A. I don't want to take more time from my colleague Sudhir. So a couple more slides that you'll see here were from the advanced spectroscopies that we support through our FTIR, and so we'll be doing that in a subsequent session. So Sudhir, I think I will let you do your part. Do you want to share?
All right, yep, I will go ahead and start sharing. See. There we go. All right, I'll move on to my slides. Can you see my screen, Lena? Confirm?
Yes.
Okay, awesome. All right, thank you, Lena. That was very helpful. I actually learned a few things as well. Now, on to the next part of the presentation. We're going to go over the complementary technique of Raman. Similar to what Lena presented, I'll go over the theory and basic knowledge, then show a couple of real-world examples on how the techniques can be applied. Finally, I'll also give some comparison between FTIR and Raman, just to show their complementary nature and and then to understand what information can be obtained from each of the technique. My aim today is definitely not to have you remember everything I present, but I'm hoping that I can leave each of you with at least a few points that sticks with you. And in our subsequent webinar in this webinar series, we'll have more real world examples, more data, and more information to share. So hopefully, as a cumulative series, we can give you a better value out of this. And feel free to add questions. And looking forward to the discussion at the end of the presentation. Slide. So I have one theory slide here, and again. The audience is of different levels, so it may be something that you may have seen many times. For some, it may be slightly new. So I'll try to go quickly here. Raman spectroscopy is an optical technique which where a sample is excited with a laser most of the time, and the energy is scattered by the sample, and that is analyzed. Again, although Raman and FTIR both probe the molecular vibrations, one of the fundamental difference between the techniques is that, as Lena explained, FTIR measures the absorbed or measured the transmitted light and then used it to calculate the absorbed infrared light, whereas Raman looks at the interaction between the excited laser and covalent bond within the molecules, by using the scattered light. Raman is sensitive to molecules that are polarizable and sensitive to biaxial modes of nonpolar covalent bonds. It is also very effective in looking at highly symmetrical biaxial, and I do have one example at later in my slides. In terms of the theory, if you look at this Jablonski diagram, the molecules excite up to a virtual state when photons strike them, and we've seen some form of others of this diagram, right? So the Rayleigh scattering, the one shown here on the left, is where the energy of the incident photon and energy of the scattered photon is the same, which is also called elastic scattering, and this is obviously most common one. The two shown here on the right, the Stokes scattering and anti-Stokes scattering, happens in about one in inelastic scattering, and these happens very rarely. So just to give you a very rough perspective, inelastic scattering happens to about 1 in a million photons. So both Stokes and anti-Stokes scattering are called Raman scattering, and between these two, Stokes is more common than the anti-Stokes. In terms of theory, I won't go beyond that, but again, coming back to that 1 in a million photon information, as you can already imagine, if you're putting a huge amount of light onto a sample, then you're getting very less Raman signal out of it. So the signal itself is the Raman itself is not a sensitive technique, but because of that, it is actually very selective, and it has its use because of that. And again, those will be the information I'll go over. So in terms of the instrument, here is a very simplified diagram of inside of a Raman spectrometer or a Raman microscope. It's one common diagram here. Again, I like to stress that only a very few photons go through Raman scattering. The light source itself is very important. You have to flood the sample with a lot of light. So for that purpose, lasers have become the ubiquitous light source for Raman excitation. So as you can see here, in this particular example, we're using a green laser. Here's a beam splitter that bounces the light onto the objective. It focuses onto a sample here, and the Raman scattering, as well as all the elastic scattering that goes back to the objective, are collected. So at this point, we're collecting both Raman as well as the reflected scattering green light in this case. Goes through the filter, and this is where the excited light is all filtered out, and only Raman passes through. And depending upon your instrument, it could be a pinhole or a slit or a combination of both. A few mirrors just to direct the light, and then grating, as we all know, is used to separate into a spectrum or different wavelengths. Bounces onto a mirror, then onto a CCD detector here, which will give you a Raman spectrum. So in terms of use of laser, there are many common ones, and I've listed a few that are common for 55 nanometer, 532, 633, 785, 1064, which is also a common infrared source that is also used. In terms of Rayleigh filter, 50 wave number cutoff, the filter here is more common, but again, depending upon your use, that can be varied as well. Slit, grating, and detector is almost always a CCD detector used for Raman applications. Moving on, Raman can provide detailed molecular information, and the bonds are best that are best represented tend to be highly symmetric bonds, commonly found in backbones of molecules or crystal lattice. In this example, what I would like to show is instead of going into deep into one spectrum here, I'd like to show what kind of big picture information can be obtained from a Raman spectrum. So let's just think of this particular peak here in the middle. So if you're looking at y-axis various, and then you're looking at the intensity of the peak or the spectrum, which can be calculated, which is used to calculate the concentration of a certain species that you're analyzing. If you are looking at the width, decreasing and increasing, then the information you're getting is whether the sample is crystalline or amorphous. In this example, the sharper one here is a more crystalline form of silicon, versus the one that is very broad is from an amorphous silicon band. If you're looking at the position of peaks, then you're looking at molecular structure, very similar to FTIR and what Lena described earlier. And if you're looking at shift of a known peak, by few centimeter wave numbers here and there, then you're looking at the stress and strain fed by that particular sample or that particular molecule. As Lena mentioned earlier, the vibration technique of Raman and FTIR can be applied to a wide variety of fields. It is hard to think of samples whose information cannot be obtained using this technique, really. And here in the next actually, and in the next slide, I'll present a couple of simple but powerful examples of Raman application. This is an example of Raman analysis of sample measured through a container. As you can see in the picture, your typical chemical container. Nothing special about it. But because Raman can measure through a container, this provides a huge advantage, such as not needing to open packaging of hazardous substance, or for general quick analysis, or just to protect the integrity of the sample, as needed by the lab. To go over this particular example here, we used our benchtop Raman spectrometer equipped with a fiber optic probe operating at 785 excitation laser. The top spectrum here is the Raman spectrum of the contents inside through the container. The second is the separately measured spectrum of the container only. The third one, the one in the red, is the subtracted result, which is the spectrum of the content. And finally, the fourth one here is the masked library spectrum, which is saying that the spectrum, which is saying that our sample inside the container is for acetaminophenol. This type of measurement is quick and easy. We're done within a couple of minutes at most, and there's virtually no sample prep needed. On to our next example here. This is more on the Raman imaging, but it is no different. Really, fundamentally, it's no different than regular Raman measurement. So this is here. It's a pharmaceutical tablet, part of a pharmaceutical tablet, and pretty much Raman spectrum is taken at every point, every interval. For example, like 5 to 10 microns in both x and y axis, and from each point, the content information is extracted based on the peaks and based on the spectrum itself, and all that can be plotted as you can see in this example, where the blue part is the aspirin, the green is acetaminophen, and yellow is caffeine. So as you can see, this is extremely powerful example, and this can be used for really any sample, any kind of surface, right? Whether you need to analyze carbon fiber, you need to analyze a degradation, you need to analyze a paint chip, you name it, a painting, really, and anything can be analyzed. And just to give you an overall big picture, you can look to and use this technique to analyze components, uniformity, degradation, any impurities and defects in samples. So, coming back to the complete vibrational approach, maybe just I'll advance the whole slide here. This example shows both infrared and Raman spectrum of cinnamon acetate, which is used in fragrances and as flavor ingredient. as you can see, the spectra complement each other. Wherever the peak on FTIR is more outstanding, bigger, taller, the same peak on the Raman is smaller, and vice versa. So as mentioned earlier, Raman is good for very looking at the symmetric bonds such as C double bonds, C here, whereas FTIR is not as good. But on the other side, when there are asymmetric bond like the carbonyl here on FTIR, which is very distinct and clear, there's not much in Raman. So the message here is these two techniques are complementary, and together you can know a lot more about the samples. And one of the questions I get a lot is, when do I use Raman and when do I use FTIR? My answer usually is, first, whatever instrument you have access to, go with it, right? Because that's the easiest thing to do. But again, for almost all, every case, if you have both, or if you have access to both, if you can get to both, then you will get a more complete picture. And in our future webinars, we'll go over more real world examples where one may provide slightly more information versus the other. But again, having together is always a winner. A quick summary slide to go over some similarities and comparison between FTIR and Raman. And this is, I wanted to put the slide to give a big picture for an user, and not going too much into the theory, because we know fundamentally they are different as well as similar in many ways. On FTIR, you're measuring the absorber to transmitted IR light. The lab light source is a broadband infrared source. On Raman, it's measuring inelastically scattered photons, and the laser light source is a single wavelength laser. In terms of sensitivity, FTIR is more sensitive because of the high amount of energy from the source. Raman is less sensitive because, as described earlier, it's a photon deprived technique, but because of that, it is highly selective. As most of us may already know, water is a big enemy of FTIR. So sample containing water or high amount of moisture, it will mask majority part of the spectrum. So it is often advised to dry the sample if possible to do FTIR analysis, as well as heat will also affect the FTIR data, because the infrared itself is heat, and any outside heat will interfere with it. On the Raman side, because we're dealing with looking at such a small amount of Raman, any ambient light will really interfere with Raman signal, as well as fluorescence from the sample is a big enemy for Raman. In terms of type of sample, FTIR is good for symmetric vibration, and although not for many samples, they may not need any sample prep compared to Raman. There may be a few steps that may be needed. All right, that completes my brief overview of Raman spectroscopy, and also comparison of FTIR and Raman. Before we get to Q&A, I'd like to turn your attention to the available resources we have for users for all levels. The Thermo Fisher Spectroscopy Academy has a lot of valuable content, such as ebooks, videos, application notes, and even lesson plans booklet that contains laboratory experiments. You could scan the QR code on the page here, or simply search Thermo Fisher Spectroscopy Academy on the web to go to this website. I'll skip over. If you need this later, we can come back to this slide for the QR code.